In the next set of videos, we're going to be looking at interpolation, and in particular, interpolation in one dimension. We'll move on to multi-dimensional interpolation in a little while. So what does interpolation mean? Basically, it means to use a limited number of function values to predict the value of the same function at other points within the range of your data. So you're taking some data that you're knowing and you're trying to estimate what that function might be at places where you don't know the data values. So, for example, in this example here, we know the data at the blue points, and the question is, well, what's the value of the function at the point x is equal to 2? So interpolation is the process of trying to estimate that. Where might you use interpolation? Well, interpolation arises in a lot of different places in engineering, the physical sciences, all kinds of different places. So, for example, let's have a look at this figure on the left here. This is a digital elevation model of a number of different data points. So those blue points there are measured, and if we then want to fit a surface to that to actually look at what the terrain looks like completely, we need to interpolate between those data points. On the right-hand side here, we have a rainfall measurement map, and so each of those black dots there represents a rainfall measurement in a particular area. We may want to know what the expected rainfall is at some locations that are away from the measurement points, and we would need to interpolate the data that we have to make an estimate of that. So these are just some of the places where you might use interpolation. Interpolation consists of two different steps. The first is curve fitting, and basically what we're doing with the curve fitting is we're fitting an analytical function to the data. We'll come back and describe in quite a bit of detail how to do that in subsequent videos. Once we've got that curve, the second step is to estimate the function values at other points, and so we're going to use this fit that we calculated in the first step, and that's what interpolation means. How do we do the curve fitting? Well, if our data is precise, in other words, we have a great deal of confidence in how good the data is, the fitting curve should pass through the data points. So if we've got these blue points here and we come up with some function that passes through the points, this then is interpolation. Now what we've done in the past, in Eng 1060 in particular, is look at the case when the data exhibits noise. So if we were to look at the points down here and we tried to do an interpolation, in other words a function that fitted through all these points, we'd probably have some function that kind of like did all kinds of weird excursions, and the results that we would get using that to interpolate would be really bad. So in the case where we have noisy data, we would use a least squares regression, and we're not really going to talk much about that in this unit. We also need to understand the difference between interpolation and extrapolation. So interpolation is when the value that we're looking for is within the range of the data that we already have. Extrapolation is when the required value, the values that we're looking for, are outside the range of the data. And extrapolation is a much riskier business. For example, trying to figure out what the stock market is going to do next week based on what it's done in the past 6 months. As a little example on the right-hand side here, we have 3 data points. These are these 3 red points here. And if we were to fit a parabola to those points, that parabola would go down to the right like that. But in actual fact, the true curve might be completely different and it might go up. So we can see that the further we extrapolate away from this point here, the bigger our error is going to be. So extrapolation is something that we need to be very, very wary of doing. Both interpolation and extrapolation are based on the function fit passing exactly through the data points. So if we want to do interpolation, the data should have as little associated error as possible. And of course, it's not always possible to do that. And sometimes it's even difficult to understand how much error your data has. So you need to keep these things in the back of your mind. And it's important to understand that interpolation is different to doing a least squares curve fit. One thing that confuses students a little is this idea of interpolating from data points and interpolating to a set of data points. So interpolation, as we've already sort of said, consists of 2 steps. First of all, we need to determine a function, y is equal to f of x, that represents our data. And so if our data is those black points there, those are the points we are interpolating from. That's the information that we know. Now I've shown an example here where we fitted a curve using a least squares regression rather than an interpolation, but the idea is exactly the same. We know the function values at the black points, the xi. We fit some kind of function that represents that data. That's the interpolation from. We then use that function to calculate the function values of yp at other values xp. And so the xp are those blue points there, and the yp are the interpolated values, those green dots, interpolated using our function. We don't know the function values at xp. That's what we're trying to find. Step 1, fitting the function, represents interpolation from. Step 2, using our function to calculate values, represents the interpolation to. And try and keep this in mind when we come to do interpolation, because it can get very confusing if you don't have this clearly in your mind. So fundamentally, we're interpolating from our known data points, xi, yi, to a set of data points where we don't know the data. That's the xp, yp. The final thing we need to worry about when it comes to looking at interpolation is we need to distinguish between global and local interpolation. So in global interpolation, we use all of the data that we have. So we fit one function to all of the data, and typically we would be fitting maybe a polynomial or a trigonometric function, for example, a Fourier series, or something called rational functions. We're not going to really be looking at rational functions in this unit. Local interpolation just uses data that's close to the point. So for example, we might use piecewise polynomials, something like cubic splines. We'll come to those later on. So we don't use all of the data, we just use the data that's close to the point. So for example, if we wanted to know what the function value at this red point was here, why do we need to worry about what's happening across on the right-hand side of this figure? We don't expect this data to influence that point very much. It's really going to be what's happening in the neighbourhood of the red dot that we're really going to be interested in. Just briefly touch on the MATLAB inbuilt functions polyfit and polyval that we looked at in Engineering 1060. As I said before, using polyfit and polyval is really doing a least squares regression. It's not really interpolation. So when the data is noisy, you can use polyfit, and polyfit finds the coefficients of a polynomial of degree n that fits our data in a least squares sense. Now, the one thing that we can use polyfit to do is, if we have n plus 1 data points, and we say, I want to fit an nth order polynomial to this data, in actual fact, this does become an interpolating polynomial. Because if you have n plus 1 data points, you can fit one nth order polynomial exactly. So you can use polyfit to do interpolation, but only if the n that you pass in here is consistent with the n plus 1 data points that you've passed in x and y. Then the second step of actually interpolating to, we use the function polyval, where we pass in the coefficients we determined up here in polyfit and a set of data points where we need want the values. Okay, that's it for introduction to interpolation.